we're going to deal with exponential functions now. So we'll get into what that looks like and what it means in a minute. But let's take a look at the problem we start with. Your soccer team wants to practice a drill for a certain amount of time each day. Which plan will give your team more total practice over 4 days, over 8 days, and explain your reasoning. So we have plan 1 is 5 minutes a day and then 1 more minute each day. So if we say day in minutes, so this is plan 1. So on the first day, 5 minutes a day, so we got 5 minutes and then 1 more for each day. So 7, 4, 8. All right. So the first part is over 4 days. So let's make our plan for each one, and then figure out at least that part. So plan 2, 1 minute today, and then twice as much time each day as the previous day. So plan 2, we got days and minutes. So 1, 2, 3, 4 is what we're after. So on day 1 we got 1. We're going to double that to 2. We're going to double 2 to 4, double 4 to 8. Okay, so after 4 days we're exactly the same. And you wouldn't think that, because on the first day all you got to do was practice that drill for 1 minute. And so if we continue our plan, let's finish plan 1. So the next part was up to 8 days. So 5, 6, 7, 8. So I'm at 9, 10, 11, and 12. So 8 days we're at 12, 4 days we're at 8. All right, look out. 5 is now at 16 minutes. 6 is now at 32. 7, we're up to 64. And at 8, we're at 128 minutes. 128 minutes is just over 2 hours, okay? Just over 2 hours. So I hope you really, really like that drill, whatever the drill is, for a certain amount of time each day. Because if that drill is going to go on for 2 hours and 8 minutes, I hope you like it. Okay, so by far, our winner after 8 days, 128 minutes. So what we see is now we talk about, we've done all the stuff with linear, right? So it increased by 1. So my slope is 1, right? M equals 1. Because we have a +1 difference every time we go. And that's what we use when we talk about arithmetic. We talked about linear. Then it goes 1 by 1 by 1. So if you look at it this way, this is +1, this is +2, this is +4. So we notice that it's nonlinear. And then what we'll talk about, what you'll see is that it is exponential. And that's how it's growing, is exponentially. And all right. So we take a look at our exponential function. We have a times b. B is the base, so b has some x as the exponent. So we can use some different values, and we'll take a look at, as I play the video, take a look at the b value is going to change what happens to the graph. So right now we see that b is 3, which is greater than 1, so we see this graph right here. So watch this as it goes, and we'll try and answer some of these questions. Okay, so pointing out a and b. So what happens to b as, or what happens as b increases? So we take a look at our graph, and you see that whole thing just moving up faster, faster, faster. Okay, so right now we see it's going left to right, it's increasing, and as b increases, it increases faster. But what about as I slow it down? So watch the value of b here. Pretty important. So what happens when b equals 1, plain old 1? So what does that look like? Does that still look like exponential, what we started seeing? And then what happens when we go under 1? Okay, when b is less than 1. Okay, you see the whole thing kind of turn around. So what does that mean? And that's what we're going to talk about through the rest of our examples. Alright, so a key concept, and this is what we're talking about, 7/6 exponential functions. Okay, so we're talking about a times b, and b is to the x power. A cannot equal 0, because we know anything to the 0 power is 0. B has to be greater than 0, so that means no negatives, right? Okay, and no 0. B cannot be equal to 1, because what happened when b is 1? Remember that we got the straight line, so that it was linear. Okay, because we want this to be exponential functions. Linear functions are linear exponential functions, right? So we're looking at growth here. We see that graph growing. right? And it's all based on that b value. And then we see it as a decay, so things are breaking down and getting half and half and half. Okay, so those are the key concepts. So first thing we're going to do is be able to identify. So just like we did, these keep changing by 1. Right, that's the x value. That's typically always going to happen, plus 1. So what's happening? So 1 to -3, -3 to 9, and 9 to -27. Well, this is times 3, and this is times 3, this is times 3. Okay, so is it an exponential function? Yes. Okay, because we were able to say that it's times 3 is the rule. So whatever we started with, we're going to multiply by 3. So we look at our got it now. So again, I have plus 1 here. Okay, I have a change of 0. I have a change of 2 and a change of 2. I'm not even sure what to use as far as multiplying, because this is times 1, but this is times 3, and that's going to be times a whole mess. So we're going to say no. Okay, so our explanation is based on what we showed on the table here. And if we take a look here, I can make a table of values. So if I used x and y, so let's say 0, 1, 2, just to get an idea. So if I put 0 in, 6 times 6 to the 0 power is 1, 1 times that is 3. 6 to the first power is 6. 6 times 3 is 18. Okay, so we start to get... Alright, and if we square it, so we got 36 here. 6 squared is 36 times 3. Alright, that's going to give us 108. Alright, so what we notice this time is that it's times 6. Yeah, we can keep going if we want to, but I know from the way that it's set up, that's a key, but if I was unsure, by making a table and saying this, so yes, and the rule is times 6, and that comes from our base right here. Alright, now we're going to get into actually using. So where does this stuff ever get used? Population growth is a great example. Suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles each week. So this part we need. I'd probably get my highlighter out. That's better, more appropriate there. Alright, so the function f of x equals 30 times 2 to the x power gives the population after x weeks. How many beetles are there after 56 days? Why do they do this? They always do this. Okay, you got to make sure you're reading. Okay, doubles each week, 56 days. All right, 56 divided by 7 days in a week. So we're talking about 8 weeks. All right, so now 8 weeks is what I want to use back in my equation. Doubles each week. So this is my equation. So f of x equals 30 times 2 to the x power. We want f of 8. 2 to the 8. We got f of 8 equals 30 times 256. So our final answer is 7,680. So 56 days, that's what's going to happen with your flower beetles. Okay, exponential grows very quickly. Okay, so we're going to have to be using our calculators, not a problem. Another reading problem involving our populations. So f of x equals 20 times 3 to the x power. So before I even read the problem, I knew I'm going to have to use that equation. So let's go back and backtrack and slow down. We're going to slow down the speed up. Initial population of 20 rabbits triples every half year. Okay, triples every half year. Okay, so that means x is going to stand for every half year. Function, they gave me the function. I already pulled that part out. Gives you population after x half year periods. Okay, so x is standing for half years. How many rabbits will there be after 3 years? Again, I don't know why. I just want to make sure you're reading the problem. So if we have this, what's going in for x? So every half year after 3 years. So how many half years are there in 3 years? Well, there's 6 half years. So 6 is going in. So we just have to finish this up. So we have 20 times, let's get 3 to the 6th power, 729, so that answer times 20, 14,580. Okay. So again, make sure we're reading. We know the equation we want to use, make sure we understand all the parts. next thing we want to do, or the third idea today is we want to be able to graph our exponential functions. So we're going to make a table of x and y values. And since we're not really sure, let's use -2, -1, 0, 1, 2, and plug those things in. So if we plug in a -2, keep in mind this is going to be 3 times 2 to the -2. So that's 3 times 1/4. So that's 3/4. So I start to get an idea of what's going on here. So this is going to be 3 times 2 to the -1 is 1/2, so that's 3/2. So I'm just going to start to highlight the actual ordered pair that I'm after here. If we plug in 0, anything to 0, so now I got 3. If we plug in 1, 2 to the first is 2, and then 2 times 3 is 6. And 2 squared is 4, 4 times 3 is 12. So we get an idea of what's going on. That means I'm going to start with some low values and get some very high values. So I'm going to put my x-axis down a little bit lower. We're going to start back at -2. -2 is at 3/4. And this will be 1 and 1/2. So at -1 we're at 1 1/2. At 0 we're at 3, so I'm right on the y-axis. At 1 I'm at 6. So 4, 5, 6. Okay, and then at 2 I'm going to be up at 12. That kind of runs off the page a little bit. So let me change colors. So we know it goes something like this. Okay, and it's going to continue on that upward rise. So we get an idea. So all of these we're going to have to make a table and check and see how it looks. We know a couple things. We know since we're talking about 2 to the x power, okay, the b is 2. So we know it's going to be positive. It's increasing. And then as we increase that, it's going to increase a little bit faster because the 3. So a couple of things we noticed. All right, down in the bottom half then, we're going to make a table again. So maybe -1, 0, 1, 2 would be enough. So x and y, so we plug that in. So keep in mind 0.5 is the same thing as 1/2. So 1/2 times 3 to the negative first power is 1/3. So we're actually dealing with 1/6. If I put in 0, I got 1/2. If I put in 1, that's 1 times 3 is 3, and half of 3 is 1/2. And then if we plug in 2, so we'll have 3 squared is 9, and half of 9 is 4/2. Alright, so I kind of use up some of the space for this, that's fine. But I see it's increasing, so I'm going to put my x-axis a little bit lower. Just for the sake of having enough space for it. At -1, we're at 1/6. At 0, we're at 1/2. At 1, we're at 1/2. And at 2, we're at 3, 4, 5. So 2, we're at 4/2. So again, we're increasing, and we see that number going up. All right. So as we make our table for b, give me a second to jot that down. We're going to go through the exact same thing. And why don't I just change colors? I'll put the table over here, put the graph over here then. So x and y. So again, let's use -1, 0, 1, 2. It's the same thing. If I put -1, that's 1/3, and 1/3 times -1/2. So what you'll notice is we're going to get -1/6. If I put 0 in, I have -1/2. If I put 1 in, okay, so that's 3 to the first power times -1/2. So we're going to get -1/2 or 1.5. So we're going to get all the same values, but negative. So that means we're decreasing as we go. So if I start at -1, we're at -1/6. So -1 is at -1/6. 0 is at -1/2. 1 is at -1/2. So -1/2. And at 2, so we got to extend down, 3, 4, 5. We're down at 4.5. So we see is that a value, as it changed from positive to negative, actually just made the whole thing flip-flop. Okay, since everything else in the equation was exactly the same, that's all we have to do. So again, we want to just get the practice of dealing with the negative exponents like we have been doing, and then flip those over. So make a table and plug it in. Alright, so same thing, we're talking about computer mapping software. I think all of us have seen this through GPS, whether it's on our phone or a separate item. So in an area view, to more detail, the function 100 times 0.25 to the x power models the percent of the original area of the map shows after zooming x times. So if we want to graph the function, so we're just saying y equals 100 times 0.25 to the x power. So we would just make a table. So let's go with, let's start 0, -1, 0, 1, 2. That ought to be good enough to get some values here. So -1, so I'm taking, this is going to be 1/4 to the -1 power. So we're taking the reciprocal of 1/4, so we get 400. If we put 0 in here, we're at 100. If we put 1 in here, 0.25 to the first power is 0.25. So 1/4 of 100 is 25. And if we put 2 in here, so 0.25 squared times 100 is 6.25. So these are our points as we zoom in each time. So if they said original and zoom 1 time, zoom 2 times, so that's what they want us to go through. So we really didn't need our -1, but I just want you to get the idea, you really see what's happening. So really we're just dividing by 4 each time. We see that? So 400 divided by 4 is 100, 100 divided by 4 is 25, 25 divided by 4 is 6.25. So we want to catch that part. So we see it's decreasing. All right. So x is 0, 0 is at 100. So if I say this is 100, 0, 100, so obviously this is way too big to make a nice actual scale, but if I said 1, then was 25, so that'd be about 1/4 of this. So I'm going to ballpark that here. And 2 is at 6.25, so based on the scale that we have. So this thing is really dropping off, okay, as far as the size. And remember, -1 back here would be up at 400, so we'd have to quadruple whatever scale we had here. So just get an idea of what it looks like. And it's so big that it's hard to get the arc to it because it drops off so quickly. Alright, we want to give these a try. We'll start class by talking about these answers. So if you can give some of them a try, that'll be helpful. Otherwise, we'll go through it. Same thing with the bottom half of that page, but these, the mixed review, that's what I talked about in class. That part you can do. This is all review material. And if you have questions, we can answer them in class.